All right, recording is rolling. Welcome to Monday, April 17th. Ooh, I have something special for you guys today, a theory of relativity. So we're going to get to Einstein relativity. There are going to be some really weird abstract ideas involved in this. It's going to stretch your imagination, but it's going to be a fun ride. All right, and where I want to start with this actually is it's going to look like a weird tie-in, but hang on to this idea that I'm about to show you because it'll tie in later. All right. So back when I was studying for what used to be the state exam back when I was in high school, there was this question that involved two people in a race. Right? And let's say we got a start finish line right here. Right? And I got a couple of guys. Right? This guy's gonna race. Right? And they're about equally as fast as each other. They usually tie. Right? I'm gonna call this guy Alan and this guy Bob. And they're looking at this tree off in the distance. Right? And say, hey, let's run around that tree and back to the start finish line. And whoever makes it back first is going to win the race. Okay, so straightforward, right? Okay. But they have different strategies. Alan's strategy is to run the first half of the race at 12 meters per second. Now that's ridiculously fast for a human, but this is just a numerical exercise, right? Okay. So for the first half, right, then he's going to round the tree. Then he's going to be pretty winded. And he's going to run the second half back towards the start finish line at 8 meters per second. Second half. All right. Bob has a different strategy. Bob's going to pace himself and run 10 meters per second for the entire trip, for the entire race. Right. Oh, I forgot to tell you guys how far they're going. Turns out the distance isn't going to affect who wins the race, but I'm going to run some numbers with you guys. So let's say this distance is 120 meters. Okay. So question for you guys is, who wins the race? Does Alan, who runs really fast and then comes back a little slower, win the race? Or does Bob, who paced himself the whole way, win the race? Okay. Oh, yeah, okay. Okay, and it's not a tie. So somebody does win this race. Somebody does win this race. Right. Let me see. Let's see. Show hands. Right. How many guys think that Alan wins the race? How many guys think that Bob wins the race? Ooh, I'm seeing more hands for Bob. You guys are right. Bob wins the race. Let me show that to you guys. So you guys know that distance equals speed times time, right? One of the first things we ever did in this class. So could I rearrange that and get time as distance over speed like that, right? And whoever wins the race, wouldn't that be like the shorter time? The shorter time would win the race, right? Because they go the same distance. So looking for shorter time. So let's see what the times are. Time, Alan, for the first half is, well, it's 120 meters at 12 meters per second would be 10 seconds to get to the tree. But then time Alan for the second half of the race would be 120 meters back at only 8 meters per second, which is like 15 seconds. If you add that up, the time for Alan was 25 seconds. Right? Versus Bob. Bob runs the entire 240 meters, right? 120 there, 120 back, right? At a constant 10 meters per second. So time Bob is 24 seconds. Okay. Yeah. And in fact, that Bob has a shorter time means he wins the race. Okay. Now you can play around with these numbers. You can make this distance anything you want. I intentionally made it so that like the average of these two speeds comes out to Bob's speed, but the guy who paces himself is always going to win the race, right? You guys see that? Okay, so just general principle there. All right, now let me tweak that scenario a little bit. Right, let's say instead of guys running at different speeds, right? What if instead you had a river next to a lake, right? And the river is going to be flowing, let's say left to right. It's got some downstream that's going left right. Okay. Right. And there's a couple of guys in some boats, right? One guy has a boat on the bank of the river. One guy has a boat on the bank of the lake. Right. I say, hey, let's race all the way down like to that distant tree and back. Right. So they're both going like the same distance again, just like Alan and Bob. Right. Only one is in a moving current and one is in still water. Okay. Now, who's going to win? Let's say they can paddle equally as fast, while they usually tie the whole deal, right? who's gonna win this race? The guy in the river or the guy in the lake? Lake? You guys say the guy in the lake? Yeah, because it's the same principle as Bob pacing himself, isn't it? Right? You guys see the same principle? Right. Okay, so yeah, the guy in the river, by the time he gets down to this tree, he'll be like winning to the halfway point, right? He's down really fast. Then going back, he's fighting an upstream battle, right, against the current, right? So it'll take him forever. Versus the guy in the lake, yeah, it might take him a little longer to get to the tree, but then if he paces himself, he'll win the race overall. Okay, you guys got that? All right, now hold on to all that because that's about to come back in a minute. All right. Where's my posters? Here we go. Got some new posters been making for you guys. All right, you guys see them all hanging from the ceiling? I did post these to Google Classroom also. Okay. So let's go back to 1849. Right, no, we're gonna put the whole River Lake stuff to the side for a moment. It's gonna come back later. Okay. And 1849 was the first time that the speed of light was accurately calculated. Right? Now, people have been wondering for thousands of years what the speed of light is. It's been assumed, well, it must have some speed, but it's just too crazy fast to figure out. There was a time like the 1600s. I think there was a guy named Ole Romer, astronomer, who was watching moons orbit Jupiter, and he made a calculation that wasn't terrible, but it wasn't too great. But yeah, 1849, and this guy named Armand Fizeau comes up with this idea. He said, hey, you know what if I do this? What if I have some light source and I have a mirror that's several kilometers in the background? See this mirror right here? Several kilometers in the background, right? And I'm letting this light ray boing bounce off so that, oh, here's an observer. I guess this is observer, right? Is observing the reflection of this light ray, right? So all fine and good. Okay? And then now we're going to introduce this cogwheel. Okay, so this cogwheel has lots of teeth on it, lots of teeth, right? And if the cogwheel's not turning, then light ray goes out, comes back, say through a gap in the teeth, back through a gap in the teeth. This observer notices, sees the reflection, it's all fine and good, right? But what if you start spinning this cogwheel? What if you spin it like insanely fast so that right, any light ray that happened to hit a tooth would never make it to the mirror in the first place? So this observer would never notice it if the light ray hits a tooth. But any light ray that goes through a gap is going to come back and also hit a tooth and stop so this guy never sees it. Now, this would have to spin so insanely fast that even for light to just go this distance and back, like 2D, that's what 2D is, right? Distance there and distance back, right? This whole wheel is turned only maybe a few degrees, only enough for a tooth to cover an adjacent gap. You see that? That's what theta is. This theta is this tiny sliver, maybe just a few degrees, right? That's all it has to turn in the time that light's going from there to there, okay? Right. And if that happens, then what does the observer see? Well, the observer, again, would not see the reflection, right? And suppose you're spinning this wheel up, like spinning up, so that it reaches this special omega value, this angular velocity where that all comes into play, right? What would it look like during that process? Well, it would look like a door was like closing on the reflection, right? And then right when it exactly matched the reflection and it looked like you couldn't see the reflection at all, right? That's where, you've got the spinning at just the right speed that everything's come together in alliance, okay? And then you can use that to figure out, well, how fast was light going to make that all happen in the first place? Okay. So got a derivation here. You can put it all together and get this, right? So the speed of light is, right? Here's the distance between the cogwheel and the mirror, right? It has to travel there and back. Here's the number of teeth. Here's the angular velocity that made it all match, and pi, boom, right? So we might do that later this week. I might give you guys a good challenge problem, take you guys through that. But for now, what's important is that, okay, you guys know 1849, speed of light's been measured. Great. Okay, so we got that. Let's fast forward a few decades, 1887. Okay, there's this team of scientists, Nicholson and Morley, and they're wondering to themselves, I wonder what is the question they were asking is, I wonder what is the speed of this luminiferous ether that light must travel on, right? Now, if you've never seen this term before, luminiferous ether, that's probably a good thing because this experiment I'm about to walk you guys through, they did unintentionally disprove its existence, right? But the thought of the time, this sort of common wisdom, the common hypothesis that was going around was, well, there must be some kind of medium that light travels on. Now, you guys know, of course, that light can travel through a vacuum, but they didn't know that back then. They didn't know that before this experiment. Okay? They said, well, waves always travel through some medium, right? You can like send a pulse on a string. You can, how about how you guys are hearing me right now? Because there's air between me and you, and my voice is traveling along those, that air, maybe like a longitudinal wave, right? So, okay, well, light must travel on some kind of wave, some kind of medium. And if there's some kind of medium that light is traveling through, I'm just going to flash up my notes from last class. Okay. Let's think about relative motion of things, right? So the Earth is already spinning, right? already there. If there's some kind of luminiferous ether that pervades everything, there's already some kind of relative motion. On the night side, the surface of Earth is traveling this direction. On the day side, surface is traveling this direction. There's already a discrepancy between the Earth's motion and the luminiferous ether that they suspected existed. How about between like the spring and the autumn, right? Well, that's different sides of the sun. That could be a difference too, right? So that's what they look for. They want to know what is Earth's speed relative to this ether, right? That was their question, right? And the way they were going to figure that out was they said, let's have a light source. Right? It's probably sending out light rays in all directions, but let's follow a single light ray that's going to go to this beam splitter at a 45-degree angle. They used a half silvered mirror. So the light could partially pass through, but part of it would bounce off at 90 degrees, right? And then these mirrors are equidistant from that beam splitter. Right? So we got two paths of light that eventually reach this observer. Let's follow both those paths. One path passes through, bounces off this mirror, baboing, back to this 45-degree mirror, baboing, and to the observer. Right? The other ray light bounces off the half-silvered mirror to start with, baboing, up to this mirror, baboing, and then passes through into the observer. Right? Is it? Right. Now, they're thinking to themselves, now here's where the guy in the lake and the river comes into play, right? The lake and the river. Right? They're thinking, well, anything that has like a north-south type motion, well, that would not be aligned with Earth's rotation, and that would also not be very well aligned with Earth going around the sun. And it's like tilted 20-something degree angle, but besides that, right? So that's probably more like being in the lake, right? Where you're like pacing yourself, right? So that's probably going to show a faster speed of light versus anything that's like east-west. Well, that aligns with the spin of the Earth and also the Earth's revolution around the sun. So that's more like the situation if you're in the river. And sometimes you're going against the ether and sometimes you're going with the ether. So overall, you're going to go slower and we should detect a slower speed of light. So that when these two light rays reach this observer, you should see those two light rays out of phase. Right? You guys know light is a transverse wave. Right? They were expecting these to be out of phase. But that's not what they saw. The result was that the light rays were always in phase, which means that the speed of light was the same. Okay, well, maybe that was a fluke. So they turned this different. It didn't matter what angle they put this at. They could rotate this experiment all different directions. It did not matter if they did it day or night. It did not matter if they did it spring or fall. It didn't matter when they did it. They always got the same speed of light regardless, right? Which was really baffling. And there were some other experiments that same thing. We're seeing over and over again that the speed of light is the same regardless of your frame of reference. Again, this disproved this luminiferous ether even existed. Okay, that's where we get the idea that, yeah, light can in fact travel through a vacuum. Okay, you guys got that? Okay, well, if the speed of light is the same regardless of your frame of reference, that's going to start to cause some weird problems. And nobody was expecting that. But Einstein's thinking about this really deeply. Right? So we're going to fast forward a few more decades, or like early 1900s. And let me split my paper in half. And I'm going to label the top half Newtonian relativity. And the bottom half Einstein relativity. Okay. Now, when people just say relativity, they're talking about Einstein relativity. But I'm going to go back to last semester and do something that seems hopefully pretty obvious. Right? Let's say you're in a truck. Right? In this truck, I'm going to do the speed of the truck to the ground is like 20 meters per second. Right? So that's how fast the truck's going. 20 meters per second. Oh, got a guy in the bed. He's going to throw a ball. Right? And the speed of the ball to the truck, right, is going to be like, say, like 10 meters per second. So that's how fast you can throw the ball, right? How fast can you throw? 10 meters per second. Right? Now you're in a truck that's moving 20 meters per second. Right? So what if there's this guy out here, has a radar gun, and is detecting the speed of the ball? I'll say the speed of the ball relative to the ground. Right? So we got ball to truck, truck to ground. Now, guys, what is the speed of the ball to the ground? 30 meters per second. You very simply add the velocities, right? I mean, they're all in the same direction. Just add them, right? Vectors, right? Add them tip to tail, the whole deal, right? You do that? Right. All right, now let's enter Einstein. And Einstein's thinking about like what would it be like to travel along with a beam of light, right? And this idea that these experiments are showing that the speed of light is the same no matter your frame of reference. I'll put a truck driver in this truck, right? Now, this time, let's not think about a ball being thrown around, right? Let's say this guy turns on his headlights. So the headlights turn on, right? And the speed of the beam of light is, I'm going to call it c. You guys know lowercase c represents the speed of light, right? Okay. Which back in 1849 determined to be about 3 times 10 to the 8 meters per second. Okay, so crazy fast. Right? So 3 times 10 to the 8 meters per second, like that. Right? Okay. And I'm going to get something crazy here, but this is just crazy thought experiment. What if the speed of the truck, the truck, was like the speed of light? Right? No, not that's ever. We've never gotten anything to move anywhere near that. Well, besides like maybe like protons or something. But let's just run with it, right? So we got this thing moving at half the speed of light. Right? Then here's this observer out here. Right? Maybe he brought along his Bezoe cogwheel with him. He's going to measure the speed of light. Right? The guy inside the truck measures the speed of light. This guy outside measures the speed of light. Right? Now the guy inside the truck, maybe he measures the speed of light from his own light beams. He gets the speed of light is c. Right? The guy outside the truck, let's see if you guys are following. Let's put it all together. This guy says the speed of the beam is what? Is c. That's it. Is c. All right. So both these guys agree that the speed of light is the same. They both say it's c. Right. So it did not add like the baseball did with Newtonian relativity. Like Isaac Newton would have said, oh, well, it should be 1.5 c, but it's not. It's just c. That's what the experiments are showing. That's what Michelson Morley showed. Okay. Right, you guys get that? Right. So everybody agrees that the speed of light is speed of light. Now, if you think that's really weird, then you're right. That is really, really weird. So Einstein sat down and he's thinking about this even more deeply. He's saying, well, hang on. So you're telling me that if one guy, if two people have different frames of reference and they both agree on the speed of light, right, that has this weird implication, this really weird implication. Let's see what he was thinking here. So right, you guys are gonna get to see this twice. Right, I've got a video demo version of this, so I'll walk you guys through it here, and then you'll see the video demo. Right, so you get to think about this twice. Right, let's say I got this guy inside the box car. Right, so he's got a red hat, he's got a clock with him, right, stopwatch. Right, okay. You put this flashlight on the ground, which is gonna shine a beam of light up. Right, and this beam of light from this guy's frame of reference, his point of view, what does that light do? This light ray just goes straight up and straight down. Boing, see it bounces off the mirror off the ceiling. Right, is it? So boing, straight down. Okay. Took some time to do that. Went to the speed of light. All good. Okay. And he maybe measures the speed of light, and he gets the speed of light as c. Great. So, right now, this guy inside the box car in this train, okay, does he know if the train is even moving or if it is moving, how fast it's moving? Can he feel how fast it's moving? Yeah, you guys are saying no, right? That's one of the first things I taught you, probably in August, right? Was can you feel the spin of the earth right now? No. If you're a passenger in a car blindfolded at I-95, can you feel if you're going 50 or 60 or 70 miles an hour? No, you have no idea. You feel accelerations, but you can't feel speeds, right? So this guy doesn't even know if the train car is in motion. You know who does know? This guy outside the train car wearing the green hat, and he's got this green stopwatch, green clock. And so let's put the train in motion. Let's say the train is going at speed v. Right? You see that speed v? So on the move, right? So this guy outside the train car, if he could also see what was going with the beam of light, he wouldn't actually see it just go straight up and down. He would see it go on this diagonal path, boing, up and down, right? Is that what he would see it do? Boing, right? So these two guys, even though they agree on what the speed of light is, even though they agree on the speed, they disagree on the distance move, right? The guy inside the train says, oh, it didn't go far, just went up and down. The guy outside says, no. It went off like on this diagonal, right? Now, if you just split this problem in half, so we just watch the beam light go up, right, up to the ceiling. Okay, you guys know distance is speed times time, right? So speed of light times time, speed of light times time, right? But if they agree on the same speed, they must disagree about how much time has elapsed. So now we're getting to something called time dilation, where when you're in motion, time actually ticks at a different rate. You see that? Right. Now, how far did the train move? Just the speed of the train times time, dt. Right. So let's put it all together. Can you do Pythagorean theorem with this? Pythagorean theorem? The square of the hypotenuse is the sum of the squares of the legs. Right? That's exactly what this says. This is Pythagorean theorem. You guys can do that, right? Right. And then what I might want to know is, well, what is one guy's time in terms of the other guy's time? Because they disagree. Their clocks are beating at different rates now. One guy's in motion, one guy's not. They have different frames of reference. So I skipped a bunch of algebra steps from this box to this box, but you can do the algebra and get one guy's time in terms of the other guy's time. This T naught refers to the guy inside the train. This solid T refers to the guy outside the train. Right? And there's a disagreement. Right? Okay. Now, what's this whole square root in the denominator? That's called the Lorentz factor. Now, I want to poke around with this a little bit. Let's test the boundaries of this. So, what if, because like, what's the fastest that anyone has ever moved? Last class, I think we came up with, well, maybe like escape speed from the Earth going to the moon, right? Maybe like the Apollo mission. So it's probably the fastest anyone's ever moved relative to anyone else, right? And if that's true, then even if you plug in the escape speed of the Earth for here, it's so tiny compared to the speed. What would that be? Let's see. What is escape speed? I think it's like 11,200 meters per second, something like that. Compared to 3 times 10 to the 8, right? That's like 0.000037. Right? That's not even considering the fact that it's being squared. If you square that, now it's like I got point string of zeros and a 1, right? So it's so crazy. Like you wouldn't normally notice this effect. Is what I'm saying. Now this effect is important for some reasons you'll see like down the line, like later this week. But for just like any conventional travel or even the Apollo mission, you wouldn't normally notice this. Right? Now, do astronauts effectively travel forward in time? Are they sort of time travelers? Technically, yeah, in a sense, but even an astronaut in International Space Station, like there for months, only travels into the future like a fraction of a second. So it's really like hardly anything. Right? But how about this? What if v went to 0? Which, I mean, even escape speed compared to speed of light is pretty close to 0, right? Right. What does this condense down to? Because what is 0 divided by c squared? 0. What is 1 minus 0? 1. What is the square root of 1? 1. So t naught divided by 1 is just t naught. Hey, and then t equals t naught. That's to say everybody agrees on how much time has passed. Right? You guys see that? Right. So as long as v, this speed, is a non-relativistic speed, which is all that people have ever traveled relative to anyone else, then everybody agrees on how much time has passed. Right? Again, it's a pretty subtle effect. Right? Well, let's go to the other extreme. What if you were to reach the speed of light? Have you guys ever heard you can never travel the speed of light? Right. So how this breaks down is anything that is massless always travels at the speed of light, including photons. Right? Light travels at the speed of light. Right? But anything that has mass, like you, me, anything else, can never reach the speed of light. Let's see what this equation has to say about that. What if you plugged in c here? What is c squared over c squared? 1. What's 1 minus 1? 0. Square root of 0. 0. What's anything divided by 0? Undefined. It's going to blow up, right? And as you approach speed of light, let's say this is like 99% of the speed of light, so you're getting pretty close to it. This would asymptotically approach infinity, right? So if you were to like get up to the speed of light, what would that look like for you from a time point of view? It'd be kind of like you were time traveling into the future. And anybody who was watching you, it would look like you kind of like froze and came to a stop. Right? That's what it would look like. Okay. No, there's more to that story too. So hang tight for that. But here, I think it's a good time to switch over and play twin paradox for you guys. You guys ever heard of twin paradox? The twin paradox? All right, let's check out the twin paradox.
Once upon a time, there was a pair of identical twins, except they were not so identical. One enjoyed the settled life on Earth, while the other was more wild and adventure-seeking. One day, the wilder one decided to embark on a journey into deep space. The two embraced before parting. The rocket traveled at near the speed of light straight into the uncharted dark depths of space. It took him 5 years to realize how much he missed his twin brother. He turned around and headed straight home. Another 5 years passed before he returned at last to Earth. Upon landing, he ran to reunite with his long-separated twin brother, only to find him no longer his twin but an old man. During his 10-year journey, 50 years have passed on Earth. He finally discovered what he truly valued more than adventures. The end.
Wait a sec.
What?
Go back, way back to the beginning.
Okay.
Like, I thought they were the same age at the beginning. How did they end up being so different in age?
That would be an effect of time dilation. Not in that way, at least. So let's imagine a train traveling really, really fast, and our explorer hops on while our settler remains behind. Now imagine that there's a light bulb fixed onto the train cart. As seen by the explorer, in order for the light to go from the light bulb and back, it only has to travel up and down.
Alright.
But the case for the settler when he's looking at the train is different. In order for light to return to the light bulb, the settler sees it traveling diagonally with the train.
Oh, that's like when you're in a car and you're throwing a ball upwards. The ball returns to your hand because it only goes up and down. But to someone on the street, the ball actually has to travel with the car to return to the passenger's hand. So the ball actually travels farther than it appears to the passenger.
Yep. But there's no time dilation because the speeds of the ball are different. If the car's not moving, the ball only goes up and down. When the car is moving, however, the ball also travels forward with the car. So it is essentially thrown diagonally upwards. The forward motion added to the up and down makes it travel faster, covering the farther distance in the same time interval. Light, however, is different. No matter what frame of reference you're in, light travels at the same speed. C, the speed of light.
No duh, light travels at the speed of light.
Anyway, going back to the train, the two observers see the light tracing out different paths. The explorer sees the light travel a distance, and the settler sees the same light travel a farther distance. Since light travels at the same speed, it would take longer for it to cover the distance the settler sees. So the same phenomenon to the settler would take longer time to happen than it would to the explorer, and so time with the train would appear to dilate.
But doesn't the same light argument apply to the passenger in the car? Like, if you put a light bulb in the car?
That's true. But in comparison to the speed of the car, light is so fast it is almost instantaneous. So technically, time in the car is dilated, but the change is hardly perceivable.
Oh, so if time is dilated as long as the frame is moving in respect to another frame, then can't you say that time is dilated for the settler in the explorer's frame?
Here's the problem. A moving frame is not enough. You need an inertial frame, which is a frame that travels at a constant velocity. For an accelerating frame, which does not travel at constant velocity, time dilation will not happen.
That would be when the explorer stops and turns around to go home. He has undergone acceleration.
Yep, you could also argue that the Earth undergoes acceleration as seen by the explorer on the rocket, but only the rocket physically experiences acceleration, so you cannot argue the other way around.
I thought everything in relativity is relative to each other.
Well, everything, relatively speaking.
All right. Okay. So hope you guys enjoyed that. All right. Now, if this is true, though, okay, so just replace the train with the rocket, and there you go. You got twin paradox with the rocket twin and the Earth twin. Right? Now, if this is true, though, I'm just going to flash my notes again from last class. Right? Well, that sets up some other problems that is going to lead to some other equations. Right? How about this? What if it's distant future? I got the Earth here. I got a distant planet here. Let's say the distance is like 10 light years to this other planet. You guys know a light year is the distance it takes light to travel a year, right? So, okay. So a beam of light, it would take 10 light years to travel. Like a radio wave, it'd take 10 years to get there, right? And let's take off on a rocket and we want to go explore this planet. Let's say we're just doing conventional travel. We haven't like mastered space-time fabric or anything. But let's say we can get this rocket up to like 99% the speed of light. I know, that's crazy, but let's just run thought experiment, right? 99% the speed of light, right? Well, from anyone who's on Earth, like based on Earth, this rocket's going 99% the speed of light. It's going to take a little over 10 years to get there, won't it? A little over 10 years, right? But remember, Earth twin, that's the guy who got really old. If you're a rocket twin, remember you say, well, hardly any time's passed at all. Maybe like a year. Well, I have to run the numbers, but let's run with that, right? Maybe like a year, right? So this guy says, oh, it took a year to get there. Well, how do you only take a year to go like 10 light years? If the distance isn't in fact 10 light years, because it's like compressed. So the entire time that rocket twin is in this rocket headed towards this planet, he sees this distance as not 10 light years, but something much shorter than that, right? Something much shorter. So there's not only a time dilation, but there must also be a length dilation, length contraction that would go hand in hand with that. That's going to lead to these formulas here. So I've got these three special relativity formulas. Right? Now this top one was derived from that train simulation you guys saw. Right? We got Earth twins time, rocket twins time, and the Lorentz factor. Boom. Okay. Let's jump down to this very bottom one, length dilation. Well, that's like if you're along for the ride with rocket twin, right? Everything seems compressed. All distances seem compressed. In fact, everybody seems shorter to everyone else. If you're in the rocket, you think the distance to your destination is compressed. If you're outside the rocket, let's say you're Earth twin looking through a telescope, you think the rocket is really short. Everybody thinks everybody's compressed, right? Now, if you're along for the ride, you don't notice anything weird about your own rocket. You're just along for the ride. Everything's all fine and good, right? So it's just different frames of reference. Everybody looking at everybody else. Okay, finally, there's this momentum dilation. You guys remember from Newtonian mechanics, momentum is mass times velocity. That's what this says, right? Momentum is mass times velocity. Okay. Now, as long as you're at non-relativistic speeds, right, then this Lorentz factor is approximately 1. It's all fine and good, Newtonian, right? But maybe I'll spoil a little bit of the story from latest particle physicists over at Large Hadron Collider, for example, they'll speed up protons near the speed of light. It's like 99.9 something percent the speed of light. So they run into this all the time, where they've got these protons going around the synchrotron, and there appears to be like increased momentum, like too much mass. Well, we only put in like a gram of material. Why are we getting like 10, 20 grams of material? Right? Where's this coming from? And it's this relativistic effect. Okay, let's look at a graph of that middle one, that momentum dilation, a graph. Okay. So relativistic momentum. Right. So what is your momentum as a function of your speed or your velocity? Right. Well, Isaac Newton would have said, well, momentum is mass times velocity. Right. He would have just followed this dashed line. And if you were to approach the speed of light, what would your momentum be? Isaac Newton would have said, oh, well, mc, of course, because you just put a c there. Right. Blah, blah, blah. Right. Now, again, that works as for non-relativistic speeds. But if you follow this Einstein dilation, okay, where you're divided by this Lorentz factor, right? Again, as v approaches c, this fraction approaches 1. 1 minus 1 goes to 0. It won't be exact, maybe like 0.0001, right? Okay. The square root of something close to 0 is, again, very small number. And if anything divided by, this could be rest momentum, right? Anything divided by like 0.0001, it's going to blow up really big. It's going to blow up really big. Right? It's going to asymptotically approach infinity. Right? Fill in a couple other parts of the story too. Right? So as you approach the speed of light, right, not only do you seem to be moving forward in time, so you would watch the universe age very quickly around you, and everyone else watching you would feel like you like frozen young, like rocket twin. Right? Lengths become contracted. Maybe I should name one for that. If it was length contraction, it would look like this. Right? That's like this formula. Right? So the universe spatial dimensions would disappear, right? And you would appear to gain infinite mass, or well, like infinite momentum, but right, so some version of that, right? It's what it would look like, right? So from the point of view of a photon, this is one of these questions that kicked us off to begin with when Einstein's thinking about this. You could make the case that from the point of view of photons, there's no such thing as space or time, because anything traveling at the speed of light, which photons do, spatial dimensions go to 0 and time goes to 0. Okay. All right. Minkowski space-time diagram. Okay, here's a fun one. And so we're really working with 4 dimensions here, but I guess our brains are better at handling 3 dimensions, and I only have 2-dimensional paper to express this on. So this x and y axes could represent spatial dimensions, right? Maybe there's a height dimension, but let's ignore that for a moment. Right? This vertical axis, think of it being time. Now I know it says speed times time. The reason for that is to make these all the same units, meters, and then speed times time would also be meters, right? But think of it basically like time, right? Time's ticking ahead, right? So all of us right now are at the origin right here. We're at the origin of this space-time diagram, right? And if you just sit still and you never move, then you're not changing your spatial direction, but you are traveling forward through time. So it's like we're traveling this way, right? Along this line. That makes sense? That's what all of us are doing right now. We're just sitting at rest. We're not changing our spatial coordinates, ignoring the motion of the earth, blah, 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 right? Right. We're just moving forward through time, right? Now, if you do start to get up and move, then you do change your spatial dimension with time. But the fastest you can move would be the speed of light. I know it's weird to put time on the vertical axis, but let's just run with it, right? Right. And the faster you can approach, what do you approach this dashed line? And this dashed line represents the speed of light because, well, B equals C at that moment, right? And this is also one of the advantages of having C times T, right, on this axis, is because this dashed line would be specifically at a 45-degree angle. In fact, all light particles have to be traveling exactly along this 45-degree angle, right, at their own speed of light. But anything with mass can never reach that. Right, so this has consequences as to cause and effect, right? Like if you send someone a message or have some kind of cause and effect, or push and pull on something, right? Anything that ever led you to where you are today, like sitting at your desk, right, had to have happened somewhere inside this cone, right? Anything that happened outside this cone here could never have affected to where you got to today, right? Same thing in the future. What can you have any kind of effect on in the future? Well, only anything that is inside this cone, right? So anything that is outside the cone, right, you can have no effect on, right? Because it would be outpacing, like you can never travel faster than speed of light, so you can never reach it. Right? For example, you guys see that Hubble Deep Field picture over there? Hubble Deep Field, right? Those galaxies are so far away, and because of cosmological expansion, how the universe expands, even if we wanted to send a rocket to those by some kind of conventional travel, right? Travel like 99% speed of light, whatever, we will never, ever, ever be able to reach those galaxies. So you can make the case that those galaxies are like outside this space-time diagram. Oh yeah. Yeah. Yeah, like 3 dimensions, right? 3 dimensions. So we got an x-axis. Whoops. We got an x-axis and a y-axis that are perpendicular to each other, right? There's sort of an implied maybe height dimension, but it's kind of hard to incorporate on this graph. And then there's, think of this again, kind of like a time axis multiplied by the speed of light. You also get like a kind of spatial height dimension. But so it's trying to sort of represent 4 dimensions, but yeah, it's kind of a 3-dimensional type graph. Yeah. All right. Let me switch over and play you guys a video on Minkowski. Where's Minkowski? Here we go.
We can now graph light using our space-time coordinates. For this, we use the distance light travels in 1 second for the units on the x-axis. This gives us the line running diagonally up the right side for light moving in the positive direction. At this scale, we cannot distinguish between the speeds achieved by snails, animals, cars, planes, and rockets from the line that represents standing still. Here's the line for protons at the end of the Large Hadron Collider's linear accelerator, traveling at 1/3 the speed of light. And at this scale, the line for protons in the LHC itself is indistinguishable from the speed of light. Now we can run the light line up the left side for light moving in the negative direction. If we then extend the x-axis line to be a plane that we'll use to represent 3-dimensional space, we can rotate the light line 360 degrees to create a cone, the light cone. This is the 4-dimensional space-time graph. A point on this graph represents an event with 4 coordinates: X, Y, and Z for space, and T for time. A mathematician named Hermann Minkowski developed the geometry for Einstein's space-time, so you may sometimes hear space-time referred to as Minkowski space. The 4-dimensional length of a line in Minkowski space is referred to as proper time or proper distance. Space-time inside the cone is called time-like because the length of connected points have positive proper time. This makes all points inside the light cone reachable. In other words, it is possible for an event at an earlier time within the cone to be the cause of an event at a later time within the cone.
All right, so I might modify that a little bit, say any point from the origin point, right? Because again, you can't travel past the speed of light, so you can't pass that 45-degree angle, but right, you guys get the idea. All right, so it goes on a little bit. I think you guys get the idea. All right, let's switch back over here. All right, just got a couple more ideas to wrap up today. All right, so next one, mass energy equivalence. So if you take those formulas for special relativity, like the momentum, dilation, right, you can derive the rest energy that's associated with some mass, right? That was a question for a long time. It's like, well, people thought there must be some energy associated with just like mass sitting there, right? Like thermal and yada yada, right? Hey, kinetic potential. There must be like some kind of base energy. Right? And Einstein's equations lead to this result. Right? Now, this P represents momentum, and I mean, if we're talking about like something at rest or like non-relativistic motion, then what if you just take this P to be 0 kg/m/s, right? Because that would be a reasonable thing to do, right? Momentum's not, right? So like, what is the rest energy then based on some rest mass, right? And we got E squared equals m squared c to the 4. Well, if you square root both sides, you get, boom, this equation right here, E equals mc squared. E is energy in joules, m is mass in kilograms, c is the speed of light. The speed of light is being squared. This is called mass energy equivalence, mass energy equivalence. So all mass has some associated energy. You guys have seen this before in this class. This is the energy of nuclear reactions, right? Not conventional chemical reactions. No, because there's no mass change for those, right? They're mass conserved. But for nuclear reactions, every time you run a nuclear reaction, there's missing mass. That missing mass is converted into energy. In fact, about 20% of the energy powering everything in this room, air conditioner, lights, projection, right, comes from nuclear. Okay, so what's there? Oh, and speed of light, of course, is about 3 × 10⁸ meters per second. Okay. You guys see that? All right. And final idea, general relativity. Right, so everything I told you up to this point is special relativity. Einstein published 1905. Or, yeah, okay. Now, many years, it's like I think like 1915, somewhere there. He also incorporated mass into his theory of relativity. And the way Einstein thinks about this is he says, well, imagine there's this 4-dimensional space-time fabric, right? 3 dimensions of space and 1 dimension of time, right? Mass will actually warp that space-time. Now, what is that good for? What is this model good for? Well, it was an update, like a modification on Newtonian mechanics that work really well until they don't. Right? So let's go back to last semester for a moment. Okay? You guys remember? Here's Isaac Newton's explanation for like, well, let's say for example, why the moon orbits the Earth. Right? Why does the moon orbit the Earth? Right? Isaac Newton said, well, there's this gravitational force of attraction between the moon and the Earth. Right? Here's the model for it: force equals gmm over r squared. Right? And if you give the moon enough tangential velocity, then it'll go into orbit. Right? That's the way I taught it to you guys. Right? Works pretty good. In fact, Newtonian mechanics is good for most everything we need. You could even run the Apollo mission to the moon and back with just Newtonian mechanics. But there are some places where Newtonian mechanics starts to fall apart. Right? One of the first places that people saw this was if you look at the orbit of the planet Mercury around the sun, there's a weird perturbation that you couldn't explain with Newtonian mechanics. We'll try to make sense of that. There were a few other weird things that didn't quite make sense. Einstein with general relativity says what's actually going on is mass curves the fabric of space-time. And the moon, for example, only ever travels in a straight line, according to Newton's first law of motion, right? But it's traveling in a straight line along a curved space-time path. And that's what appears to make it orbit from our point of view. Okay. And if you simplify general relativity down to just like non-extreme cases, it actually simplifies to Newton's law of gravitation. Okay. So what else can Einstein relativity explain that Newtonian mechanics could? Right. Well, one of the first tests happened in 1919. There was a solar eclipse. Okay, tell you guys the story. Okay. So it has to do with something called gravitational lensing. Let me go back to this fabric type. You guys know this fabric here actually represents like 3D space, and then the compression represents like a time compression, right? It's like a model. It's the best I can do on 2D paper. Okay. So suppose there's a light ray that comes in, right? It passes by the Earth. Well, Earth should actually bend that light ray because space-time is bent. Right? Now, photons don't have any mass, but they do travel in straight lines along space-time, so they can be affected by gravity. Maybe that's something that Isaac Newton wouldn't have predicted as much, like that something massless could be affected by gravity, but that's not in Newtonian mechanics, right? But it is in Einstein mechanics. Einstein says, no, light could be bent by gravity, right? Even though it's massless, right? Because it'll follow this warp space-time, right? But what is actually massive enough to warp space-time enough that it could bend light rays enough that it would actually be noticeable? Well, the largest mass we have in our solar system is the sun, by far. The sun is like 99% the mass of the solar system, right? So you could look around the periphery of the sun and map, well, where should the background stars be normally? and where are they as the sun comes by? So as the sun comes by, you should like warp it, kind of like a magnifying glass, like warp it. And Einstein predicted exactly how much it should be warped. Problem is, the sun's so bright, you can't actually see the stars right around the periphery of the sun during the daytime. So you'd have to wait for when it was really dark, when it's really, when's it going to be dark when the sun's out? How about during a solar eclipse? During a solar eclipse, okay? And so the moon, or well, the sun has 400 times the diameter of the moon, but the sun is also 400 times further away. It's just a complete weird statistical coincidence of the universe. So 1919 solar eclipse, the moon just covers the sun, which it does during a solar eclipse. Photographers went out there, grabbed some pictures, and developed the photographs. And lo and behold, the stars actually were shifted exactly as much as Einstein predicted they would be, according to theory of relativity. And at that moment, it was pretty well established that Einstein relativity had replaced Newtonian mechanics as the rules that govern the universe. Right? Of course, Einstein relativity does simplify to Newtonian mechanics under non-extreme examples. All right, so that's a wrap today. We'll continue this adventure the rest of this week.